8 as the overall area. Okay, it's recording and we got sound. Okay, so let's do another one, shall we? A minute ago we had, yes sir.
That was just the area of one. Oh, like right now.
That was the area of one petal. That was all I asked for. But now that if I ask for all of it, you know that there's 4 petals, so I just multiply by 4.
All right, thank you.
That wouldn't have anything to do with the bounds of integration point. But you still stay from 0 to 2, even though there's 4 petals.
Because one petal closed up at pi over 2. Let me give you another one. Let's do another rose curve. With that marker.
You want to do that? I'm gonna play with like letter blocks.
Want to do an even or odd?
Try odd.
Okay. So how many petals? That'd be 5 petals in this bad boy. So what's 360 divided by 5? Five times 7 is 35. They're all 72 degrees apart.
That's always calculus.
72 degrees apart. So what we got to do is find the tip of one and then just add 72 degrees to get all 5 of them. All right, so what I did before is I found the angle that goes here so that the cosine hits its largest value of 1. And then around that angle, I had to find 2 consecutive zeros so that I know where the petal closes. So cosine of what number is 1? Cosine of 0 is 1. So tip of the petal occurs when 5 theta is equal to 0. So it's 0. Okay? So write down the x-axis. Always happens with cosine, no matter how many petals we have. Then we got to find out where it opens and closes. So I need to find consecutive angles around 0 at which this opens and closes. So that's when the stuff under my hand is pi halves, right? So that's at theta's pi over 10. And then we could just use the fact that this first tip is on the x-axis. It closes at pi over 10, so it's going to also close at negative pi over 10. So here's our first petal at pi over 10. We're at pi over 0. So it's 0 here, and then at pi over 10 and negative pi over 10 it closes. So there's the first petal. Then I find 72 degrees. About how big is 72 degrees? I don't know. I need 5 equally spaced petals, every one of them 72 degrees apart. Pi halves is 90 degrees, so 72 degrees is about right here. I'm gonna have another pedal up here, and then add 72 degrees to that, and I get 144. This is 180, so 144 might be somewhere around here. Then add another 72 degrees to that, 72 plus 44, or 144. 16. So this was 180. This is 3 pi halves, which is 270. So 216 might be closer in here. So there's another pedal in here somewhere. 180. I don't know, I'm just lying now. And then add another 72 to that. 298. So there's another one here. So it's going to go here to here to here to here to there. Well, each of these, God, that's bad. Well, each of those, God, this one's the one that screwed up the whole picture. Come on. What do you want out here? Each of these are 72 degrees apart. Right? But all we want is one pedal. And I found it where I can integrate from negative pi tenths to positive pi tenths, and then use my 1/2 f of theta squared d theta. So that'll give me one pedal, and then I'll just multiply by 5. And then I put my f of theta in here. Now with cosines, I can use symmetry. I can integrate and get just the top half of the pedal, put a 0 down here and double it. And I always like to be able to use a 0 as one of my limits of integration. And I choose to do that because it's wise and it makes it easier. And I'm both wise and easy. Hey, wait a minute. Now we do a Udu substitution again. Think U be 5 theta, do you use 5 times d theta? So 1/5 du is equal to d theta. These twos cancel each other out. That's always nice about using symmetry. So I'm integrating 0 to pi over 10 cosine squared of u times 1/5 du. And here's where our formula comes into play. Integral cosine squared of u is going to be u divided by 2 plus the sine of 2u divided by 4. And then that's multiplied by 1/5. We get the u back in there. U was 5 theta. Times 5 theta gives me a 10 theta. And now I put my bounds from 0 to pi over 10. Theta. Let's do this trig function first. If 10 theta is here, I get the sine of pi. That's 0. 0 is there, I get the sine of 0. That's 0. So at both endpoints, this is 0 again. So all I'm going to do is put pi over 10 in there. So I have 1/5 5 times pi over 10 divided by 2. So that's pi halves. Pi halves divided by 2 is pi fourths. So I get 1/5 of pi over 4. That was for one petal. We said we had 5 petals, so the overall area is 5 times that. So the total area is just pi over 4 square units of area. So let me ask you a question. What if I just looked at the picture and said, well, I can get the whole picture by integrating from 0 to 2 pi, right? It covers the entire polar plane. So I do all those steps, but I'm doing them from 0 to 2 pi. So I don't have the 5 times anymore. I got 0 to 2 pi here. Am I going to get the same answer? I'm sorry? Yeah, it's not going to be that way. Because look, what if we integrated 0 to 2 pi? So I still have the formula that has a half here. I got 0 to 2 pi. I have the cosine squared of 5 theta. I still do this bit, so I'm going to get a 1/5 out there. So I'm going to have a 1/2 times 1/5 times. Then I've got all this, 5 theta over 2 sine of 10 theta over 4. The 2 pi goes here, I get the sine of 20 pi, that's still 0. Sine of 0 is still 0, so that's still 0. Put a 2 pi in here and the 2's will cancel. And so I would get 5 pi. 5 pi times 1/5 is pi times a half. It gives me 1/2 pi. Why? Why is it not the same? Think in terms of what a multiplier does to the picture in rectangular coordinates. It repeats itself, right? This is repeating itself. I've got too much area because I traced the picture too many times. In this particular example, it looks like it traced the picture exactly 1 lap too many. So it drew that picture out from 0 to pi instead of from 0 to 2 pi. So you got to be careful with this thing. So what I will always do when we're dealing with rose curves is I'm always going to find the area of one petal by finding where it opens and closes and where its tip is. And then if I want the total area, I'll just multiply by the number of petals. That way I don't have to worry about tracing the graph out more than once. Okay? And it's usually only this kind that you need to worry about. Okay, so let's look at what we do if we want to try to find the area in between two curves. So let me just put that in your notes. The danger. You get too much. Okay, if you just integrate 0 to 2 pi to rho squared, you get too much. And I can't predict how much too much. Sometimes it's double, sometimes it's more, sometimes it's some fraction. So I can't predict how much, so I just do one pedal at a time. Find the area that is outside the cardioid R is equal to 2 plus 2 sine of theta, and inside the circle. R is equal to 6 sine theta. But in order to find it, you got to at least look at it. Let's draw the picture and see what it looks like. So I've already labeled it as cardioid. I want you to get to where you recognize the equations. A circle just has a number plus times a trig function. But then if you take that circle and scale it away, then that's going to make it heart-shaped. Okay? So if you're going to graph this cardioid, pick some nice numbers to plug in for the theta. So maybe you can find out what the cardioid looks like just by plugging the angles in for the coordinate axes. Try that. 0, pi halves, pi, 3 pi halves. If you're still not sure, then plug in the pi sixes, because the sine of the pi sixes are going to give us a half. So see if you can get a graph of this cardioid, and I'll just sit here and stare at you. Or see if you can graph it just by plotting the angles at the coordinate axes. Otherwise, plot a few more. Okay, so let's get that cardioid. Usually sines are going to be symmetric to the y-axis. So if I plot r is 0 or r is pi, I get the same thing. Sine of 0 and sine of pi are both 0. I'm sorry, I didn't mean r, but theta. R is 0 when theta is 0 and pi. R is 1 when, actually it's not going to be 1, is it? It's not going to be 0. At 0 and pi, that's 0, so R is 2. When theta is pi halves, R is going to be 4. And when theta is 3 pi halves, what did you get for R? It'll be 0. So that cardioid goes, at pi halves, it goes out here to 4. At 0 and pi, it's over here at 2. And then it goes back here. So here, to there, to there, and then back. Okay? All right, now this circle is going to be, what did I say this was? This was 4. So let me make this bigger because this is going to be a circle of diameter 6. So let me put 6 right here, and then draw a circle like that. And we want outside the cardioid, but inside the circle. So we want this area right here. The angles of intersection are going to play a role here. You're going to find those. I need to know what theta is when they intersect. So set those two equations equal to each other and tell me what at least the one in the first quadrant is. Five or 6, very good. Put this over here and you get 4 sine theta is equal to 2. Divide by 4, so I'm looking at the angle which sine is a half. And in the first quadrant, that is pi over 6. So then this one would be 5 pi over 6. So we're going to have to figure this in between stuff out. So if I ignored the cardioid, if I just ignored the cardioid and integrated from pi over 6 to 5 pi over 6 of this circle, I'm getting too much area. And the amount of area that I'm getting is exactly that part of the cardioid from pi over 6 to pi over 6. So I'm going to find that area and subtract it out. So remember our formula, 1/2 r squared d theta. So I'm going to have to put 1/2 f of theta squared d theta of the circle, and then subtract out 1/2 f of theta squared d theta of the cardioid. Agree? Or we can put them all in the same integrand. We can kind of think of, remember that when we computed these areas, we partitioned the region with little pieces that were shaped like pi with rays from the origin. So if I look something like that, I'm getting the circle. So if I look at that little piece, I need to take this and subtract that off, right? So my plan is to do that my area is equal to 1/2 of the integral of f of theta squared d theta. But if I've got in between two graphs, I can do it this way. Right? Because I'm going to have two separate intervals when I put them in the same integram. Where this is the outer and this is the inner. So, the way we can set this one up is we can integrate from one point of intersection to the other. So from the smaller angle to the bigger angle. The outer one is the cardioid. And the inner one is the circle. But what if I wanted my lower limit to be 0 and I want to use symmetry? Would that work? That wouldn't work. I would have to, if I want to use symmetry, then I would integrate from here to here and double it. What's wrong? Did I write something wrong?
Isn't the outer circle?
It is. Why didn't I just follow my own instructions? You know what's upsetting me is this color. It's that longhorn baby shit color. When I say ship when I'm wearing a mask, it really sounds like that other one. Baby ship. So I'm blaming it on the mask. Oh yeah. Okay, you're right. The outer one is the circle, the inner one is the cardioid. But like I said, if I want to use symmetry, I can't go from 0 to pi halves like I did before. I can go from point of intersection to pi halves and then double it. Okay? Is there any benefit to doing that? I like getting rid of the half in front. So I'm going to use symmetry. I'm going to change this to times 2, and that's pi halves. So I'm going to do 2 times 1/2 integral pi 6 to pi halves of 6 sine theta squared minus 2 plus 2 sine theta squared. So now we're going to do some squaring. Those cancel. The 6 squared is 36 sine squared theta. We'll get those parentheses to hold that minus sign. And when you're squaring this, you're multiplying it with itself, boiling it out, so you're going to get a middle term. But the lead term is going to be 2 squared. The middle term is twice this product. That product gives me 4 sine theta. Do that twice, and I get 8 sine theta. And then the last term squared is going to be 4 sine squared theta. Let's distribute the minus sign, collect like terms. I'm going to have 36 sine squared minus 4 sine squared for 32 sine squared theta. Then I'm going to have a minus 8 sine theta, and then minus 4. Are you with me to there? Do you remember yet what the integral of sine squared of theta is? See, it's easy to memorize. Theta over 2 minus sine of 2 theta over 4. So this one's our formula. we know? Integrate sine of theta and we get minus cosine of theta. Integrate 4 and we get 4 theta. And then we have to take all of that and evaluate it from pi 6 to pi halves. All right, so let's see if anything simplifies for me. If I multiply by 32 here, I get 16 theta minus 8 sine of 2 theta. And then I get plus 8 cosine theta. And then I have a minus 4 theta. So let's go ahead and take the minus 4 theta away from that and make this a 12 theta right here. And then let's evaluate that from pi 6 to pi halves. So I don't think we're going to get away cheaply and get a bunch of zeros. I don't think we'll get a bunch of zeros anywhere. We'll get a couple of zeros, but not a bunch of zeros. So let me plug in pi halves. And I'm going to plug in pi 6. Now I can find my zeros. Sine of pi is 0. Cosine of pi halves is 0. And that's it. The rest are going to take on some values that are non-zero. So my final answer is going to be 6 pi minus 2 pi. Minus the minus gives me plus 8 square root of 3 over 2 minus 8 square root of 3 over 2. So life is good. The 8 square root of 3's over 2 add each other out. 6 pi minus 2 pi gives us a total area of 4 pi.
That was way too much effort.
That was too much effort? It's not like we're like digging ditches or something. Digging ditches is a lot of effort. Okay, let's do what sounds like a real easy problem. Let's overlap 2 circles. Let's take a 4 cosine theta and overlap it with 4 sine theta, and let's find the area of the overlap region. Find the area common to 4 cosine theta and 4 sine theta. So 4 cosine theta is going to be a circle of diameter 4, tangent to the origin, but symmetric to the x-axis. The other one is the same, but symmetric to the y-axis. So the region of overlap is right there.
Oh, that sucks.
Because
You're gonna have the same, like,
What do you mean the same angle thing?
The same theta, like.
Okay, so they do intersect with a nice same theta. Can you tell me what that theta is at intersection?
I'll get back to you.
No, where's the sine the same as the cosine? Pi over 4. See, I scaled it the same way, so that's going to be pi over 4. That's not that bad. That's not the part that sucks. Here's I'll outline it in red. So imagine that region being cut with rays emanating from the origin. So there goes the rays from the origin hitting the curve. When you're below that dotted line, which circle are those rays hitting? The sine. When you're below this, all the rays are chopping up the region of the sine curve. But when you're above it, they're chopping up the region of the cosine curve. So there's not one integral involved. There's two integrals. From 0 to pi fourths, you have to integrate this one. From pi fourths to pi halves, you have to integrate that one. Or you can thank me for choosing the same scaling factor and making those symmetric to one another. So that this region down here has the same area as that region up here. If I didn't do that, you would need two integrals. Did I see why? So without the symmetry, we need two integrals. With symmetry, I'm going to find the area of the region that I shaded and just double it. So this is symmetric. You're going to find the area between 0 and pi fourths and double it. But again, if I chose different numbers here, I'd get a different angle, and you'd have to do two different integrals. Okay, so if I put 2 here, maybe. If I put a 2 there, then they're probably going to intersect somewhere else. All right, so I'm going to use the symmetry and get it's the upper circle here. I'm going to take 2 times 1/2. That circle starts at 0, and then it closes up to our point of symmetry at pi fourths. And that's the shifted upward circle, so it's that one. There might be one on your web work where you have to do with 2 integrals. Yes,
So if we have to do the one here, we can also do pi
pi fourths to pi halves, and then the other circle. In this example, now web work generates random numbers, so this might have to be an arc something something, an arc tangent of something. So be on the lookout for that one. I think I put it on this web work. Okay, so anyway, it's not that bad. Now we can just integrate. So 2 times 1/2, it gives me a 1. This is 16 sine squared of theta. Is a constant, integrate sine squared. We have a handy dandy formula. Theta over 2 minus sine of 2 theta over 4. From 0 to pi over 4. So put the pi over 4 in for theta. Pi over 4 over 2 is pi over 8. 2 times pi over 4 is pi halves. Sine of pi halves is 1, so I get minus 1/4. Put the 0 in there and I get 0. Put the 0 here, sine of 0 is 0. So that's my area right there. Send the 16 through, and I get 2 pi minus 4 square units of area. And I've already done the doubling. Okay?
You made it sound like that was going to be a lot.
I know. I wimped out because of your comment on the last one that it was too much work. I wimped out and I put the same scaling factor there, and I really shouldn't have. I should have put a smaller circle and a bigger circle, and then it's work. But then I remembered I put that on web work, so why not just let you do it? All right, so I can do these until my head falls off, but you'll learn better if you try it. So what I'm going to do is start talking about the next section. Okay? All right, so what we're going to do is find the length of an arc of a rectangular coordinate graph, and then we're going to do the same thing with a polar graph. So let's click back into rectangular coordinates. So in section 6.4, arc length. So first we're going to go in rectangular coordinates. Arc length is measuring the path along the curve. Say I'm interested in knowing the path along this curve. There's the x-axis. From x is equal to A to x is equal to B. So if I just had a little person with one of these little iWatches, I'd make them run it, and then they can look at their distance on their iWatch. Boom, that's how we do it. Well, we don't have a little person with a little iWatch. So what we do is we cut this path into itty bitty teeny tiny line segments. Because I can find the distance or length of a line segment with the distance formula or the Pythagorean theorem, right? If I have a straight line from x1, y1 out to x2, y2, that's point P and that's point Q. The distance between point P and Q is what? The sum of the squares of legs, right? Find out how long that leg is, square it, find the length of that leg, square it, and that gives you the length of the hypotenuse squared. You take the square root, and there it is. Horizontal leg squared plus vertical leg squared, square root. So we're going to do that. We're going to chop up the interval from A to B into itty bitty teeny tiny pieces. So that in those little pieces, that segment is essentially a straight line. So I make a lot of tiny cuts. I'm going to make them kind of big so you can see them. But this is magnified 10 gazillion times so that the human eye can see it. And I'm going to connect those with a straight line, find the distance, add it to that, add it to that, add it to that. And if these are close enough, then it traces the curve out perfectly. And the way we're going to make it close enough is we're going to take our partition, we're going to shrink the width of it by taking the number of points to infinity, which is going to give us some sort of interval, right? So let's look at, say, the kth partition. So that the ordered pair here is, say, xk, yk, and the ordered pair here is xk plus 1, yk plus 1. So we have the length of the kth partition. So we take the difference between the x's and we square them. We take the difference in the y's and square them. So I have yk plus 1 minus yk, xk plus 1 minus xk. Those are squared, added together. I'm not going to write that. I'm just going to write delta xk, delta y. Okay? So it's going to be delta xk squared plus delta yk squared under the square root sum. And now I'm going to factor out a delta xk squared. I'm going to put the square root sign on last. So if I pull it out of here, I get a 1. If I pull it out of here, then I'm actually dividing by it. So technically, this is like this. I got lazy with the parentheses. So I'm going to go ahead and put the parentheses back like that. Then I can factor out a delta xk out here because I got a square of a perfect square. Now that delta y over delta x, that's the average change of a function on the kth subinterval. Who remembers the mean value theorem? The mean value theorem was a relationship between the average change and the instantaneous change, wasn't it? It said on an interval for a continuous function, there's at least one place at which the instantaneous rate of change is equal to the average rate of change. Now, these intervals are teeny tiny, almost a single point. So it should be really easy to find where the instantaneous rate of change is the same as the average rate of change. And what do we call the instantaneous rate of change? The derivative. So by the mean value theorem, I can put the derivative in here. That's going to be the derivative of y. And now we make a Riemann sum. To get the total arc length. And that'll be yk, so that's the derivative over each subinterval. So the total arc length is going to be a sum from k is equal to 1 to n of things that look like that. And then we take the limit as n goes to infinity, which makes the delta x's go to 0. And poof, out pops an integral that has that thing as its integrand. And so the arc length is the integral from a to b of the square root of 1 plus y prime squared times dx. So this will be the derivative as a function of x. So it's an easy enough formula. It's essentially the distance formula. The only problem is there aren't many things that we can put in here that right now we know how to integrate. Right? If I started with a parabola, y is equal to x squared. The derivative is 2x. Right? If I take 2x and square it, I'm going to have 1 plus 4x squared under the radical sign. I can't do that with a UDU integral. Yeah, there aren't many integrals at this stage we know how to do. So the problems in this section are very contrived. So that once you put the derivative in here and square it and add the 1 to it, you're either going to get a perfect square, so that I can take the square root of the perfect square, or you get something that you can factor out something and have a UDU integral. And then once we learn how to do more of these, I'll show you how to handle things like the arc length along the parabola. And remember this formula, we're going to do the same thing with a polar curve, chop it up into itty bitty teeny tiny pieces next time. So if you haven't already, get section 6.3 finished, and then I'll put up a 6.4 for you once I get this section finished. Thank y'all. Any questions at home, Evelyn?
No, thank you so much.
You good?
Yeah.
Okay, I'm gonna cut this bad boy off then.
All right. Thank you. Have a great day.
Thanks.